Alrighty, so in section 1.3, we're going to describe our quantitative data using numbers. So one of the things that we're going to talk about, so here's our sub-objectives. You can look right here. We're going to calculate the measures of a center, mean and median for a distribution of quantitative data. We're going to calculate and interpret range, standard deviation, IQR. We're going to explain outliers and skewness, all kinds of stuff. You can take a look at that and see what we're doing. All right, so when we talk about center of our data is usually going to be one number that we use to describe an entire data set. And one of the ways we do that is with mean. Mean is very, 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 very common when we are describing our data. We like means. This is not a word. This is a word that you have heard before. So the mean of a distribution of quantitative data is the average of all the individual data values. Define the mean, add the values, and divide by the total number of data values. Okay, that's on the right below it. I don't know why it does this. There we go. So if we have n observations, where we have 1 observation, 2 observations, 3, 4, 5, 6, all the way up to n observations, the sample mean, x bar, when we say that x bar, it's got an x and a bar, is given by this formula. So it's the sum of our data values over the number of data values. So we're going to add all values. So we're going to add the values up right here. That's what this means. That sigma means add everything up. And this is the number of items. And that will give us one number to describe an entire data set. Now, notice here I use the word sample. Sample is something that we need to pay very close attention to, because a sample will generate for us a statistic. Oops, let me go up here. Boom. So a statistic, not like the name of the class, but what an actual statistic is a number that describes a characteristic of a sample. And then we have parameters. Parameters is a number that describes a characteristic of an entire population. I'm going to get into those words here in a minute. So they are different. They mean different things. A statistic comes from a sample, and a parameter comes from a population. So one of the things that we're going to see a lot of is this X bar, and we're going to see this Greek letter. This is the Greek letter mu, M-U, not mu, mu. Mu. This is mu. So X bar is the mean of a sample, and mu is the mean of a population. Well, then what is a sample and a population? Well, the population includes every member of the group of study. This would be the group of all individuals. All individuals. So this is going to be all individuals we want information on, or we want information for which we want information. There we go. Let me do that in proper English, not end in a preposition. All individuals for which we want information. That's a population. Now, so that would be like all Independence High School students. That would be a population. All IHS students. Everybody who lives in America. Everybody on the entire planet. All 2024 Hyundai cars produced. All laptop computers produced in May. That's a population. Now, some of those examples I gave you, you could never, it'd be very difficult to gather data on that. So a sample is only some of the individuals for that group of study. So like if I got all IHS students, that's a relatively small population. I could talk to all IHS students. However, I could not realistically talk to every single American. There's 340 million Americans. So I would have to do a sample of those. So this is a smaller group from a population that I can actually talk to. So this is a smaller group that we can realistically reach. I don't know if my spelling is right here. So if your population is too geographically spread out or it's too expensive to get to an entire population, you would use a sample. A sample is a smaller portion of a population. Okay? So populations, if you talk to every individual, then you use mu. If you do a sample, then you're going to use X bar. So that, because they are, the formulas are slightly different. But thankfully for us, we don't really need to do the formulas. All right, let's take a look at this problem. Here are the data on the number of goals scored in 20 games played by the U.S. women's soccer team. And they give us the number of goals. Let's calculate the mean number of goals per game by the team. Show your work. Okay, so this team scores 5 goals, 1, 10, 5, 2, etc., etc., etc. If I want to come up with one number to describe what I expect the U.S. women's soccer team to score, I can take the sum of all numbers, the sum of the goals, and divide that by the number of games. So I add up all the goals that were scored, divide it by 20 because it's 20 games, and I would expect the U.S. women's soccer team to score about 3.15 goals per game. That is their X bar. X bar tells me this is only a sample of the games played by the U.S. women's soccer team. It's not all the games they have ever played. It's just the 20 from one season already, or 20 games given from a specific period of time. So there's a suggestion that the games in which this team scored 9 and 10 goals are possible outliers. So when they scored here, they scored 10 goals and they scored 9 goals. Some people go, wait a minute, an outlier is an abnormality, that was a fluke, or that doesn't happen very often. So let's calculate the mean number of goals per game by the team in the other 18 games. What do you notice? So again, we did the sum of the goals divided by the number of games. Notice it's only 18 games this time because we took out the 9th and the 10th goals. So we notice that now they dropped to 2.44 goals. So we removed those high-valued goals, those high-valued games, and our average went down. So these two games increased the mean number of goals played per game by 0.71 goals. That's what I noticed. If I keep the 10 and the 9 in, my average is significantly higher. And that, what we're going to find out later, is that 10 leads me to believe that 9 and 10 are outliers because my average changed. Now, when we have potential outliers, we don't like to use mean. We like to use something called median because we find out that the mean is not resistant to outliers where the median is. So median, you may have done this in other algebra classes. So the median is the midpoint of a distribution. It's the number that's such about half of the observations are smaller and about half of the observations are bigger. So to find the median, arrange the data values from smallest to largest. Very important. I can't stress that enough. You must arrange your values from smallest to largest to find median. If the number of data values is odd, the median is the middle value on the list. Let's highlight that. That's important. If the number of data values is odd, the median is a value in the list. If the number of data values is even, our median will be a space between two numbers. The median will be the space between two values. So what you need to do then is you are going to use the average of the two values from our list. Okay, I'll show you that in a minute. So a statistical measure is resistance if it is not sensitive to extreme values. Medians are not sensitive to extreme values. So a median is always more resistant than the means. Outliers affect means more than they affect medians. If something is super expensive compared to everything else, my average will go up, but the median will not. We're going to see that here in a moment. Okay, so here are the data on the number of goals scored by the 20 games played by the U.S. women's soccer team. Let's find the median. So the first thing I do is I put the numbers in order. So here's all the 20 data pieces put into order. Now, since 20 is an even number, the median is going to be a space. So I am going to have 10 values to the left of the middle. So there are 10 values this way, and there are 10 values this way. And the median is right here. It's that space. Find the middle value. Another way of doing that is you can take 20 plus 1 and divide it by 2, and so you get 10.5. So at the 10.5 value, the 10.5 value is the median. So that's our median. So let's find the mean of the values on either side of the median. So you would add, here's my median, right there is the median. Add the 2 and the 2 together. I would get 4 divided by 2, 2 goals per game. So why is the median smaller than the mean? Well, the median is less affected by than the mean by the high goals of 9 and 10 goals. So this median of 2 goals per game would be a better measure of center than the mean. All right. So let's go ahead, and I would like you to answer questions 1 through 10. In your assignment, go ahead and answer questions 1 through 10, and then we will get back and keep going. We will compare mean and median in the next video.